Hi, I'm Mark Barsamian. In this video, I'll be discussing derivatives of exponential functions. This material is in section 3.2 of the book, more specifically page 187 to 188, and example 1, and page 191 to 192, example 3a, so bits and pieces of different parts of section 3.2. The corresponding homework is this set of 4 exercises from section 3.2. Now let's first, before starting new stuff, recall the derivative rules that we've learned about in previous videos. We have the constant function rule that says the derivative of a constant is 0. We have the power rule that says that the derivative of a power function is obtained by this calculation. And we have the sum and constant multiple rule that says that the derivative of an expression made up of a sum consisting of constants times functions is computed a certain way. In this video, we'll learn 3 more rules for finding derivatives of exponential functions. The first rule is about the derivative of the most simple exponential function, y equals e to the x. And it says this: if f of x is e to the x, then f prime of x is e to the x. That's the 2 equation form. The single equation form says that the derivative of e to the x is e to the x. That's what I call exponential function rule number 1. Now this very simple rule is found by using the definition of the derivative. Remember this limit that defines f prime. We would build the limit by using the exponential function to build those expressions. There's e to the x plus h minus e to the x over h. Now, a key early step in the computation uses an old fact about exponents, that this e to the x plus h is e to the x times e to the h. That's just a rule of exponents. A later key step in the calculation of f prime of x is a fact from higher math. In the calculation of f prime of x, this limit emerges, and the fact from higher math is that that limit equals the number 1. Now, the details of the calculation, organized by the 4-step process, are shown clearly in the book on pages 187 to 188. It's very interesting math, very beautiful, and it's worth reading. But in Math 1350, you'll not be asked to do the calculation, and I won't discuss the details here. But we will gain a better understanding of the rule if we examine the graphs of f of x and f prime of x. In the video for homework 37, we saw that it's possible to draw the graph of y equals e to the x by hand, using the graphs of y equals 2 to the x and y equals 3 to the x as guides. Here we'll just use a computer graph. So this is the graph of y equals e to the x. And the graph at the bottom is also y equals e to the x. But they're playing different roles. The graph on top is to be considered as the graph of the function f of x. The graph on the bottom is to be considered as the graph of the derivative, f prime of x. Because remember, the derivative rule number 1 for exponential functions says that the derivative of e to the x is e to the x. In other words, if f of x is e to the x, then f prime of x is also e to the x. So there are the graphs. So what I want to do is discuss why these make sense. So to do that, let's think about lines that are tangent to the graph of f of x. And on the graph of f prime of x, I want to think about y values on the graph at those same x values. So what we should think about is the numbers that are the slopes of the tangent lines up here. So let's just describe them in very crude terms. So in simplest terms, the slope of this tangent line is a small positive number. That tangent line is not tilting very much. The slope of this tangent line is a medium positive number. That tangent line is tilting up, and its slope would be kind of a medium size positive number. This tangent line is very steep, so its slope is going to be a large positive number. Now let's go down to the graph of f prime of x and think about its y values. So thinking about y values, the y coordinate of that red point is a small positive number. That point is near the x-axis. The y coordinate of this point could be considered a medium-sized positive number. And the y coordinate of this point could be considered a large positive number because that point is way above the x-axis. So look, the numbers that are the slopes on the graph of f at particular x values agree with the numbers that are the y values on the graph of f prime. Now that relationship is the relationship that you're supposed to have between the graph of f of x and f prime of x. F prime of x is the graph whose y values are supposed to be the numbers that are the slopes on the graph of f of x. So it's believable that the derivative of e to the x is e to the x. So it's believable that rule 1 is true. Rule 1 says the derivative of e to the x is e to the x. Exponential function rule number 2 is very similar to exponential function rule number 1. In rule number 2, the original function is f of x equals e to the kx. So there's a constant k in the exponent sitting next to the x. Turns out that the derivative, f prime of x, is k times e to the kx. In single equation form, we'd say that the derivative of e to the kx is k e to the kx. Now, rule number 2 is also found by using the definition of the derivative, using a slight variation on the computation that's used to find rule number 1. The book discusses this new result only in exercises in 3.2, number 61 and 62. Those aren't even in the MyLab system, so you won't see them. The book doesn't discuss this result in the reading, and it never presents it in a list of derivative rules. That's too bad because it's one of the most used derivative rules. That's why I've given it the name rule number 2, and I've put it in a green box because we'll be using it a lot in the future. So for our first example, I want to use exponential function rule number 2 to find the derivative of y equals b to the x. Well, there's a trick here. The trick is to rewrite the function b to the x so that it is in one of our forms that we have a rule for. So there's our rewritten function. We used two old rules of exponents. One is this one. The number b can be written as e to the ln of b. I'm going to put parentheses there. The other rule of exponents that we use, another old rule, is this. E to the m raised to the nth power is the same as e to the m times n power. Now we have a function whose derivative we know how to calculate using rule 2. So let's go back up and look at rule number 2. Rule number 2 says the derivative of e to the kx is equal to k e to the kx. So on the left side of the equal sign, we just have the derivative symbol, d over dx, and we have e to the kx, and there's an exponent that's the letter k. On the right side of the equation, the derivative symbol is gone, and the k is now sitting in front, and it's also still on the inside. So the left side of the derivative equation is what we currently have. We have one of those, and we're going to replace it with the right side. So there's the right side of rule number 2. You can see that the constant k is now sitting in front, and then the exponent expression is still there with the k and the x up in the exponent. Now, we've done the derivative. We can now simplify this expression. What we've done here is we've used the calculation that we did earlier. When we rewrote the function, we started with this and we ended with this. We wanted this form because that was a form we could use with our exponential function rule number 2. Now that we have done the derivative using exponential function rule number 2, we end up with an expression that has this thing here, which can be replaced with this. So our final result is that this derivative, dy dx, is this. So in other words, that's our answer. Now that is such a useful formula that it actually gets a name. It gets called exponential function rule number 3. If f of x is equal to b to the x, then f prime of x is b to the x times ln of b. In this expression, I've moved the ln of b over to the right side. That's the 2-equation form. Single equation form is closer to what I have on the previous page, closer to that. Single equation form says the derivative of b to the x is b to the x times ln of b. All right, well, for the remaining examples, I want to just do derivatives of functions involving exponents. So example 2 is just derivatives of basic functions. So for each function, we're supposed to find f prime of x. Notice, even though we have these new derivative rules, the first derivative rule that we use is an old one. This is the constant multiple rule. The next rule that we use is one of the new ones. Notice here we have the left side of rule number 1. Rule number 1 says that that expression equals this expression. So rule number 1 has a left side and a right side. The left side of the rule has the d over dx symbol. The right side of the rule just has the function. So that rule says anytime you have one of these, you can replace it with one of these. And that's our result. F prime of x is 5 times e to the x. Let's go on. Question B. Now here, look what we've got. We've got this expression. That looks like the left side of rule number 2. Rule number 2 says that that expression equals this expression. The left side, there's a derivative symbol, and there's an e to the kx. The right side, there's not a derivative symbol, but there's a k e to the kx. So rule number 2 says that we can replace this expression with that expression. So you can see that we replaced the left side of rule 2 with the right side of rule 2. And the k on the left side was in the exponent, and there was a d over dx in front. On the right side, the d over dx is gone, but there's a k in front, and the k is still up in the exponent. And at the end, we can simplify. We multiplied 5 times 7, and we got the number 35. Let's go on. Question C, f of x is 5 times 7 to the x power. We need to find f prime of x. Now look, we've got sitting here something that looks like the left side of rule 3. We've got one of those things. Rule 3 says that we can replace that with this. that is the result of using the derivative rule. What can we do now? Well, notice that we have a function, 7 to the x, and we have constants in two different places. So one thing we could do to clean this up is put all the constants in front. So I have a constant multiplying a function. Question D. The derivative of 5e to the 7th. Now, if you look back to our very first example, A, the derivative of 5e to the x turned out to be 5e to the x. So if you're thinking quickly, you might think, well, if the derivative of 5e to the x is 5e to the x, then maybe the derivative of 5e to the 7th will just be 5e to the 7th. But look more carefully. There's no x in this expression. 5e to the 7th is a constant function. So the derivative of 5e to the 7th is not 5e to the 7th, it's just 0. Question E, derivative of 5x to the e. Now here we have to be careful. Remember that the derivative of e to the x is e to the x, but we don't have e to the x. We have x to the e. This is not an exponential function. This is a power function. The variables in the base in the exponent is constant. So we should use the power rule with n equals e. Let's remind ourselves how the power rule looks. The power rule says that if you have one of these things, the derivative of x to the nth, you can replace it with this thing, n times x raised to the n minus 1. So the left side of this equation has the derivative symbol and has x to the n, has no arithmetic going on. The right side of the equation, the d over dx is gone. There's the n sitting in front, and there's a new exponent computed that way. So if I use the power rule with n equals e, that looks like this. I write down the value of n, I write down my x, I write down my new exponent. Now this can be simplified. I have a function, x to the e minus 1, that's a power function, and I have constants sitting in two places. I can multiply those together, those constants. So there's our result. The derivative of 5x to the e is 5e x to the e minus 1. Notice how similar this left side looks to this one. Here we have the derivative of 5e to the 7th. Here we have the derivative of 5x to the e. Look how different the results turn out to be. And for another comparison, look how similar this is, the derivative of 5x to the e, to this one, the derivative of 5e to the x. Look how different the results turned out to be. The derivative of 5e to the x is just 5e to the x. But the derivative of 5x to the e is 5e x to the e minus 1. So you have to be very careful when using these derivative rules. You have to scrutinize your functions. Okay, example 3 is derivatives of more complicated functions involving exponents. Question A, differentiate this mess. Well, the first thing we do is the first thing we always do. We look to see if we can use any of our very simple derivative rules. And we can. We can use the sum and constant multiple rule. Notice that constant multiple of 5 slipped through the derivative symbol. The constant multiple of 13 slipped through the derivative symbol. But the number 7 is not a constant multiple. It's a constant function. It's got to stay inside. So here we used 3 different rules. We used the constant function rule to get that result. And we used the power rule with n equals 1 to get this result. Finally, we used our new exponential function rule number 1 to get this result. So we can clean this up, and it just becomes minus 5 plus 13 e to the x. Okay, question B. First thing we do is we use the sum and constant multiple rule. So we use the sum and constant multiple rule. That multiplicative constant 5 slipped through the derivative symbol. The multiplicative constant 7 slips through the derivative symbol. And then for the next step, we prepare a space for the results of doing those derivatives. I don't do the derivatives in this step. I save them for the next step, and they're going to go here. The derivative on the left is simple. We're going to just use rule number 1. The derivative on the right is also simple. We're just going to use rule number 2. Notice when you use rule number 2, you're taking the derivative of e to the kx. So on the left side of rule number 2, there's a d over dx symbol and there's an e to the kx. On the right side of rule number 2, the d over dx symbol is gone. The k is sitting in front, and it's also still up in the exponent. Now, what we've ended up with is an expression that has a function and constants sitting in two places. Those can be combined. And there's our result. Question C. Our first step is to just use the sum rule. This breaks up into 3 derivatives. There are no multiplicative constants. Notice that this is an exponential function with base b equals 3, so we'll use rule number 3 for that. This is not an exponential function. It's a power function with n equals 3, so we'll use the power rule for that term. This is a constant, so we'll use the constant function rule for that. And then we can clean up into the final step. And our result is that dy dx is this stuff. As one last note, notice that these 3 examples that are part of example 3 all involve just finding a derivative and the same sorts of steps. Started using the sum and constant multiple rule in the first step, and then used derivative rules in the later steps. But they're presented differently, 3 different ways. This question said differentiate that expression. There was no y mentioned. There was no f of x mentioned. In the second question, a function is introduced. There's an f of x, and you're asked to find f prime. In the third example, you're given an equation, y equals some stuff involving x, and you're asked to find dy dx. So the derivative questions can come in different styles, and you have to be prepared for that. In your MyLab questions and in the book questions, you'll see a variety of styles of questions. That's the end of this example, and that's the end of the video. Thank you.